It's Paul Bamberg with script 2D, this being a D script. At some point it's going to involve real-world data, and what I want to introduce you to is the concept of sampling from a population, and then to teach you a very useful technique called a permutation test that lets you deal with situations where you have one sample from a population. So let's start with a situation where we know everything about the population and are therefore in a position to figure out how well we can do by looking at samples. We've got a 6-question test taken by a highly incompetent test taker who has a probability of only 20% of getting each question right. So what we can now do is simulate scores from 5 different tests, and the way we're going to do this is by using one of these random number generator functions in R. In this case, our sample is drawn from a binomial distribution. We're doing 6 trials, 6 questions, each of which independently has a probability of 0.2 of leading to success. So this is saying, let's draw 5 samples where the number of questions is 6, the probability of getting it right is 0.2, and let's look at the scores on these 5 tests. And our test taker 4 times in a row got only 1 question right and then lucked out and got 3 questions right. If I repeat this result, I'll get different results. On the 5 tests, the number correct was now 11021. So I have a way of simulating a small sample of test scores. And from one of these samples, I can compute some sample statistics. I can ask, for example, what is the average number of questions got correct? I'll call that X bar. What is the variance of this set of numbers? That is the mean of the squared score minus the square of the mean score. What is the so-called population variance, which is calculated when I apply the R built-in function, var, to my vector of scores, and let's see what the results are. X bar, the average number of questions correct, was 1. We were expecting 1.2, so we weren't too far off. If I compute a variance from this set of numbers, I get 0.4, but if I use the built-in variance function in R, I get 0.5. That's correct, and it's one of the seminar topics for this week, to show that when you try to estimate the population variance by using a sample variance, you divide by n-1, not by n. Now let's simulate what would happen if we did this 10,000 times. So we are going to create 3 very long empty vectors, x bars, x vars, and pop vars, and we're going to fill these up by doing 10,000 simulations, where in each simulation we will generate our set of test scores for 5 tests. We will compute and store the mean test score. We will compute and store the variance calculated directly from the numbers in that vector, and then we will ask R, what is your estimate of the variance of the population? When we do this, we're going to get a vector x bars whose length is 10,000, and you can see it's got some outcomes. First time the average score was 1.0, the next time it was 1.8, next time it was 1.2, and so on. Let's take the mean of this, 1.20316. Okay, The expected number of questions correct was 1.2, so as is very often the case, by using a large sample, we got a very good estimate of the population mean. What about xvars? Ooh, we did very badly. We expected to get 0.96, and in fact, we got 0.78. That's because sample variances come out smaller than population variances if you compute them by the mean of the square minus square of the mean formula. If I use the built-in var function in R, on the other hand, I get 0.975, which is quite close to 0.96. Remember this when you are using R. If you take some sample data and ask for its variance, what R will give you is its best estimate of the variance from the underlying population. Now let's look at a histogram of our results. There's a histogram of the results, and I can take a typical better than average value of 1.6, plotted as a vertical line, and by glancing at this histogram, you can easily see that the probability of getting an average score greater than 1.6 is not all that small, even though your expected score for this 6-question test was only 1.2. Or to put it differently, if we observe 1.6 as the mean score, we can't really rule out the hypothesis that the probability of getting a question right was only 0.2. Now, in the real world, we usually don't know that much about the underlying population. We've just got a sample. So let's simulate that situation by getting a sample of 20 scores. This is different every time I run the script. Let's make a bar plot of it. This does not look binomial in the slightest, does it? But let's treat it as if it were a population. We've done this before. We've got a data vector with 20 values in it, and we can draw samples of 5 from it. We'll draw these with replacement, so we could get the second component of the vector twice in our sample. And this is going to give us a vector which I will call scores. This is going to come out differently every time we do it. So let's do it 10,000 times. That's easy to do on a computer. I will create a great big long empty vector to hold the mean of my 5 samples, which are really resampled from this sample of 20. That's why Chihara and Hesterberg call their book Statistics with Resampling and R. So 10,000 times we will extract a sample of 5 from our sample of 20. Save the results. We've now got 10,000 results, and the mean was very close to 1. That's a big sample. It should have been 1.2, shouldn't it? No. We started with a sample where the mean was 1. There's no way we're going to fix that by resampling. Let's look at a histogram, however. And the histogram is looking very much like we got from the binomial distribution. So we've managed to reconstruct the shape of the binomial distribution by working with this sample. This is a simple example of a statistical technique known as bootstrapping, which put very simply is if you don't have information about the population but you've only got a sample, take the sample and treat it as if it were in a population. In other words, take the data frame that we get from the real world and deal with it exactly the same way I was dealing with those data frames for populations for coins and dice and cards. Now let's try a practical application of this. Suppose we're giving some tests in Harvard Yard and that the folks in Elm Yard study harder, they have a 70% chance of getting a question correct. For the rest of the yard, the probability is only 60%. So I'm going to make a vector called yard that has 30 copies of E for elm, 60 copies of Y for yard, and then I'm going to match that up with a vector called score, where in the first 30 rows, I am going to have a 5-question test with a 70% probability of correct, but for the last 60, I'm going to do it with only a 60% probability. And then I'm going to make a data frame out of the two, call it elm yard. This might be worth loading later on, so I will write it out to a CSV file. Now, what can I do with these data? Well, the obvious thing to do is to calculate the average score for elm yard from these sample data. How do I do this? I take the score multiplied by 1 if the value in the yard column was E, divide by the number of rows where the yard column is E. That's the average score for the elm yard students. And yard average is the average score for the students in the rest of the yard. You'd expect that the average score for the elm students would be a little bit higher. After all, they have a 70% chance rather than a 60% chance of getting the question correct. And in this case, you're right. Their average score is bigger by 0.2. But now suppose we were faced with these results and had to answer the question, is this significant? Does this show that elm students are better test takers on the average, or was this just a matter of luck? Here's a way to answer that question. We actually know the population, so we can repeat the simulation we just did 10,000 times. So 10,000 times we will do the same thing. We will generate some scores for elm and yard, compute the averages, compute the differences, and save them in an initially empty vector named diffs. What's the mean value of that? The mean value of that is very close to 0.5. Why? Because the elm students have a 10% higher probability of getting a question right, and over the course of the entire test, that will lead to their getting half a question more correct on the average. Let's make a histogram of this, and now you see, well, yeah, the mean is 0.5, but in many of our simulations, the elm students got almost 1 question more right on the average, and there were even occasional situations where they did less well. How often did they do less well? Well, if I take the mean of diffs less than 0, I see that this happens about 1.6% of the time. Now let's look at this differently. Suppose we have just our single sample. We've got 30 elm scores. We've got 60 scores from the rest of the yard. We read that back in from the file that we carefully saved. Compute as before the elm average, the yard average, and then say the observed difference is 0.2. And now we've got to figure out whether that's likely to be significant or not. Here's an ingenious way of doing this, and if you're going to learn only one statistical technique, this is the one I recommend to you. You say, we have a specific sample of 30 out of 90, the 30 students in Elm Yard. But suppose instead we just chosen at random 30 of these freshmen, a mix of folks from Elm and from the rest of the yard, and had carried out exactly the same operation. Computed the average score for this new group of students. I'll call it Elm average, but these are chosen randomly from throughout the yard. Compute the average score for the rest of the yard. Take the difference, and you can immediately appreciate that because the population of 30 was chosen at random, this difference is as likely to be negative as positive. If you take a random sample of 30 students, they're equally likely to do better than or worse than the 60 remaining students. Well, on a computer it's easy to do this 10,000 times, so let's do it. Let's carry out exactly the procedure that we used, but now using a random sample of 30 students. And let's look at a histogram of the difference. This histogram looks pretty symmetrical around 0. We expected that. And now comes the wonderful step. On this histogram, we display the difference that we actually observed. That's represented by the vertical red line. And if you look at the part of the histogram to the right of this, you can say, if I pick a random sample of 30 students, fairly frequently, I'm going to get a score difference that's just as large as what I observed, and therefore I doubt that this difference between Elm and the rest of the yard is particularly significant. And in fact, I can compute the probability that a difference that large could have arisen by chance, arisen by choosing a random subset of 30 students. All I have to do is compute the average value of a quantity that is 1 if the difference exceeds the observed value, and I find that that happens about 24% of the time. Statisticians call this a p-value. So in this case, we would say the p-value, the probability of observing this large a discrepancy by chance, is about 25%. I don't really think this result about the superiority of Elm Yard is particularly statistically significant. Okay, now let's try the same thing with real data rather than fabricated data. These data were collected in a pub in Minneapolis. Since Laura Chihara teaches in Minnesota, they may well have been collected by one of her students. They are saved in the file beerwings.csv. Let's load this up and look at what we've got. In the data frame BW for Beer Wings, we have 4 columns. The ID of the pub patron, the number of hot wings they consumed in the course of the evening, the number of ounces of beer they consumed, and their gender. I can easily figure out there are 15 men and 15 women, and for these 2 groups I can now compute the average beer consumption. This is just like computing the average test score for Elm Yard. The average beer consumption by the males was 30.4 ounces. The average beer consumption by the female patrons was only 22 ounces, and the observed difference was 8.4 ounces of beer. It looks as though in Minnesota, men consume more beer than women. But is this difference significant? Well, we're going to use exactly the same approach. Just as we replaced our 30 Elm Yard students by a random sample of 30, we are going to replace our male beer drinkers by a random sample from among the 30 beer drinkers. It could include 15 men, it could include 15 women, it could include 8 men and 7 women. All of those possibilities, or each way of selecting the patrons, is going to be equally likely. How are we going to do this? Well, we've got this gender column in our data frame, and I'm going to say to sample from it. This is sampling without replacement, and what it will do is just take a sample that looks like this. It's going to have 15 M's and 15 F's, because I've asked it to draw 30 samples from a vector with m and f, and to do it without replacement. By the time it's done, it's selected m 15 times, f 15 times, and the only thing we don't know is the order in which these are going to show up. So this is going to be a permutation of the original vector. That's why this is called a permutation test. Now, these m's don't really go with men. They go with a random sample of the pub population, but I'll call it male average and female average. Compute the difference. And in this case, because I used a random sample, this is as likely to be negative as it is to be positive. Now what are we going to do? We're going to repeat it 10,000 times. So 10,000 times, and we're going to store the result in a vector called diffs. We will permute the gender column to get a gender column that has m's and f's randomly distributed. We will compute the average beer consumption for this simulated male population. For the simulated female population, we will store the difference. We will check that the difference is close to 0. By symmetry, it had better be. And we will display a histogram of the difference. So this is what happens if you take the 30 people in the pub, select 15 of them at random, compute the beer consumption for the random sample, subtract off the beer consumption for the remaining 15. Now let's show on this histogram what we actually observed. And you can see the probability of getting a difference with a random sample that's larger than the 8 ounces we observed is fairly small. Exactly how small? Well, it's the p-value, and it's about 3%. What you do with this, in my opinion, is up to you. I'm a mathematician. I'm not a statistician. I'm not a sociologist. What I'm saying is that if you choose 15 of these 30 patrons at random, the probability that you will observe this large a difference is only around 3%. And it's up to you to decide on the basis of that whether you think the observed difference between male beer drinkers and female beer drinkers is significant. By the way, if you went to 50 different pubs observing this and picked the pub where the discrepancy was the largest, you'd almost surely be able to find a discrepancy this large. So that's a permutation test. We'll be using this over and over again throughout the course, and it's going to be quite interesting to see to what extent we can simulate the result of such a test without heavy computation by using some mathematical results.